contact us a couple of months ago, and his interests overlap a lot with the interests of some of us over here. In particular, he's interested in social media and natural language, and his talk is going to discuss a combination of those topics. So with that, let me turn it over to him. Questions will be at the end. Raise your hand if you have a question, and then Soyoung, who's actually I should introduce Soyoung. She's somewhere in here. She's the moderator for the AI in Society list and talks this semester. So she'll be the one who will be calling on you to ask your question. Thank you. So Vibhor, you can begin.
Yeah, thank you so much for the introduction. Let me share my screen. Yeah, I hope you can see my slides.
Yeah, I see them, so you can begin.
Yeah, cool. So, hello everyone. It's a pleasure meeting you all. So the title of my presentation is Understanding Online Conversations and Tackling Online Harms. So let's begin the presentation by looking at this conversation from Reddit. So if you read this comment, this bottom bold comment, it says, it's funny to see the hamster that starts to act up in their little tiny brains after saying that too. So if you try to understand this, it just says that, okay, hamster, which is an animal, have like tiny brains, right? Which doesn't look like anything wrong because it's a well-known fact. But if you look at the entire conversation above, you would get to know that actually the conversation is about girls and women. So here, indirectly, hamster refers to women. And that's why this comment is misogynistic in nature or like a hate speech. So my motivation behind this example is basically to motivate the idea that conversational context really matters, and like, be it as a human being or as a machine learning model, they actually need the context of the conversation in order to basically like predict whether a comment is a hate speech, or it can be useful for a variety of other NLP tasks as well. So idea behind my research is basically to develop those graph-based approaches that basically like try to capture this conversational context, which could be useful for the overall online conversation understanding tasks. Uh, Moving ahead, as we all know that online conversations have like a lot of problems such as hate speech and toxic content, misinformation, fake news, and so on, right? So how we approach this problem is is like this. So currently, like most of the approaches or state of the art models in the literature, they just look at like individual comments and try to flag them as like hate or toxic content, but they don't look at the conversation as a whole, which they might be like missing a lot of context, as in the example that we are seeing right now. So conversation involves threaded replies, right? Where a comment can have like multiple replies and then replies of replies and so on. So we look at conversation as a graph. For example, this one, where the root node of a graph is actually the start of the conversation, and then the replies, and then the reply nodes, and the reply, and so on. So basically, this directed edge represents that this comment is replying to this comment, and so on. So basically, it takes the form of a of a tree structure, but it won't be like a binary tree, but it can have like multiple nodes replying to a single node and so on. Yeah. So for this for online conversation understanding, we initially look at like two important tasks. One of them is polarity prediction, and the other one is hate speech detection. So polarity prediction goes like this, which is like given an online discussion or a conversation, the task is to predict the polarities. That's like whether a reply is an attack or supporting the parent argument. If you look at this figure, let's say A, B, C, D, and E are arguments in a conversation, and argument B replies argument A, whereas argument C and E replies argument B, and so on, right? So in this case, this arrow indicates the replies, and green color indicates supports, and red indicates attacks. So argument B supports argument A, whereas argument C attacks argument B. So this is what we need to infer the polarity values for this task. So basically, predicting these polarities correctly can help us measure several properties of discussions, such as like how controversial they are, or sort of finding the winning arguments in the discussion, and so on. So for that, uh, for the polarity prediction task, we look at the Kialo platform. So Kialo is an online debating platform, which is like a formal setting of debates where we do have like a thesis, and then people can come in and comment either in support or attack of the thesis. Uh, so our dataset contains about like 1500 plus discussions with a mean of about 204 arguments in each debate. So as we see this very naive example where people are debating that whether the earth is round, and then sort of like green comments indicate that it's like supporting, and red comments or orange comment indicates that it's like attacking the parent argument. So these debates take the form of a tree structure with each reply either support or attack. We sort of observe that these Kialo debates are typically balanced. That's about like 40 to 60% are support edges, with rest being the attacks. So we also make this dataset publicly available on our dataset website of the research group. Yeah. So next problem we look at is hate speech detection, which is kind of like similar, which says that the task is to predict whether a comment in an online discussion is a hate speech or not. And as we just saw, that like conversational context really matters in those kind of conversation understanding tasks. So in this case, we look at we use the guest dataset, which is an expert annotated imbalance hate speech dataset from Reddit. And we could specifically use this data because it had like the useful information to construct the conversation trees, which was uh like what is the parent comment of a given comment and the discussion ID, let's say. So that's why we could infer the conversation graphs out of it. Next, let's look at the methodology. So as we just saw, we firstly represent these online conversations as graphs, right? Then I've been talking about conversational context a lot, but how do we actually capture that? And then we'll be discussing about the GraphNLI architecture. Yeah. So one of the ways where we could capture the conversational context is through GraphVox. So let's understand from this figure, which is like, this is an example conversation where A0, A1, A2, all of these are like comments in a conversation. So biased root seeking random walk says that like for a given node, let's say A1, we want to capture the conversational context useful for it. Then this walk is like probabilistic in nature, which is like this walk is biased towards the root node. That's why it gives the highest probability to the root node, whereas the remaining probability is distributed equally among the children nodes, right? And then probabilistically, it selects one of the nodes, one of the neighboring nodes, and and the walk goes on till the walk length L. As we saw that like these online discussions can be like very large, can have like hundreds and thousands of comments in a discussion, right? So in that case, we need to fix the walk length so as to avoid the over smoothing problem, which is like if we capture the too much context, surrounding context, then the embeddings for each of these nodes will be like very noisy, and it would like lose the predictive power for the machine learning models. The next is a weighted root seeking graph fork, which is kind of a deterministic version instead of probabilistic, which is like with a definite probability of 1 for node A2, the walk will move up towards A1, then A0, and so on. So basically, it will capture all the ancestor nodes for a given node. And we also give like a discount factor of gamma, which is like because we observe that farther the node from a given node, lesser will be its influence. So that's why influence of A0 on A2 will be lesser than influence of node A1 on A2. That's why we define this discount factor gamma. Then there could be like other ways of having these graph forks, which is like a similarity based approach, which is like we sort of derive these probabilities from the similarity scores. So we look at the similarity of a given node with respect to the nearby nodes and sort of calculate the probability values based on the similarity score, uh, so that the random walk can capture the neighboring context probabilistically. And the other one that we implemented was an attention-based random walk, which was like kind of learnable. So all the parameters that we saw, like the discount factor and the probability, those were like fixed initially. But then as part of attention-based random walk, we sort of like train a neural network to learn those hyperparameters by itself based on the given conversation and try to get the attention scores or the weights for each of the neighboring contexts so that like we can select the most important nodes for the conversational context. And all this is going to be helpful for hate speech and the polarity prediction task. Now, once we capture all of this like conversational context, we input that into the GraphNLI architecture, which is like all these sampled arguments, argument 1, 2 up to L based on the walk length of L, we input it, and then we sort of get the BERT embeddings first. And then at the end of the pooling layer, we get the corresponding sentence embeddings for each of these sample comments from a graph fork. Then this embedding U is embedding corresponding to the argument that we want to predict as hate or non-hate, whereas embedding V is the conversational context that we captured. And this is the aggregation of all of these captured nodes. And then we concatenate these embeddings, and finally a fully connected classification layer for the classification task of hate speech. Now let's look at the results. Firstly, let's look at the polarity prediction results. So as we can see that these four are our baseline approaches. So including the state-of-the-art models like BERT, sentence BERT, and even the graph machine learning models like graph convolutional networks. And we sort of, as we can see that GraphNLI actually performs very good as compared to other baseline models. And it's also performing like about 3% higher macro F1 score as compared to sentence BERT, which actually sort of tells us that conversational context really is helpful for the machine learning model. Next, let's look at the hate speech detection problem. For this one, again, if we compare the baseline models with different variants of GraphNLI, which is like a root-seeking graph walk and a biased root-seeking random walk with different aggregation strategies, let's say like summation, average, and the weighted average. So we can see that the last strategy, which is GraphNLI with a biased root-seeking random walk, sort of performs better than all the baselines and other variants of GraphNLI. So which sort of says that conversational context really matters. And since it's like a weighted aggregation, that means uh, the nearby nodes are more helpful for these NLP tasks rather than the nodes that are farther away in a discussion tree. Then we also did like error analysis in this one to sort of compare specifically the hate precision and recall because the data set was like imbalanced, right? So we saw that, so we have like three variants, a BERT model, which is a baseline, then GraphNLI, and GraphNLI small is actually a model trained on just uh, small conversations from Reddit. Small as in like conversations which have like just one or two comments, so that the model won't have any conversational context. So as we can see that GraphNLI, which has conversational context, has higher values of hate precision, recall, and F1 score. Yeah. And also we observed that uh, conversational context leads to a lot lesser false negatives and false positives for the hate speech detection task. So for example, this example, as we have been discussing, was also like falsely labeled as non-hate by the BERT model. But after considering this conversational context, the GraphNLI model was able to predict it correctly as misogynistic hate speech. Yeah. All right. So until now, we have looked at the importance of conversational context. Now let's little bit dive further and look at the subjectivity of hate speech task. So so do you consider this statement as misogynistic, which says like, do you have the skin of a 80-year-old grandma? Worry no more, just drink water. So I'm sure like some of you might consider it as misogynistic, while others would say, no, I mean, like it's a natural phenomenon. Like if you go old, then your your skin can get loose, wrinkly, and so on. So out of three annotators in the dataset, two annotators labeled it as non-misogynistic, while the other one as misogynistic. So we can see that this is kind of a subjective opinion on this task. So, but like the aggregated label is non-misogynistic because the majority of the annotators annotated as non-misogyny, right? So hate speech can even be difficult for humans to accurately annotate and have higher annotator agreement, and that's why on most of the hate speech detection tasks, often annotators get like low annotator agreement scores because like they can have like subjective opinions. And also it can be perceived differently depending on individuals perspectives and like prior experience. For example, if somebody has like experienced some misogynistic remarks before, then they would be like more sensitive towards misogyny in general rather than someone else who is not part of that community. Yeah. So our problem statement is to improve. So again, to improve the detection of hate speech, but specifically the aggregated labels. So we sort of like try to model not just the comment text, but also we try to label different annotator perspectives or different choices, as well as label semantics. For that, uh, we use this three-step methodology. First one is basically to get the annotator perspective to model them. We use collaborative topic regression, which is a topic modeling approach for getting like the useful topics out of the corpus. And then second, we integrate the label text, and then we'll discuss the AnnoBERT architecture, which is sort of like a BERT variant, which incorporates the annotator embeddings as well. So let's discuss how do we actually get these annotator representation. So this CTR model is a probabilistic model originally used in recommendation systems. So we sort of get inspiration from recommendation systems and try to see that, okay, from the hate speech datasets that we have, if we sort of try to get the unique topics out of it, and then we can capture different levels of sensitivity towards each of these topics, because we hypothesize that different annotators can have different levels of sensitivity towards these topics. So that's how, from the CTR model, we get individual annotator embeddings, which are unique representations based on each annotator's characteristics. That's why for this training task, for each of these annotator, we represent it by a fixed length vector, and each element in that vector represents the annotator's sensitivity towards a specific topic. Right. So once we get these annotator embeddings, we sort of like integrate it with label text as well, which let's understand with this same example of a 80-year-old grandma, wherein like we have like two categories of annotators, one who annotated as hit. So we duplicate this instance and then concatenate the label, which is hit, and then the annotator embeddings. Let's say if annotator 1 and 3 annotated it as hate speech, so their embeddings would be concatenated. And likewise for the non-hate annotations. But for the evaluation, we know that we don't know these ground truth levels. This is what we need to predict. That's why we just sort of like concatenate the annotator embeddings who have annotated this particular instance in the test set. Once we have all these like embeddings and the setup ready, uh, we uh, experimented with this like AnnoBERT architecture, which takes the comment text as input along with the annotator class labels, right? And input it into a BERT kind of model. Once we get these BERT embeddings, they are concatenated with the annotator embeddings as well. And these annotator embeddings, as we saw, we get it from the CTR model, like a topic modeling approach. And then after mean pooling, we get the aggregated annotator embeddings. So with text, we have two different kind of information. One is like annotator perspectives through embeddings, and then the class labels. And then we have like usual BERT feature extraction layers and the classification layer, right? So overall, this AnnoBERT is a deep learning model that integrates the annotator characteristics and the label text with a transformer-based model for specifically for the hate speech detection task. For this work, we again look at like guess dataset as we saw before, and guess dataset is like highly imbalanced, which is like they just have like about 10% instances is hate, as we expect that in the real world scenario. Whereas Dynabench is a crowd generated and annotated data set. So that's why it's like synthetic data. That's why it's like sort of balanced. But the reason why we chose these two specific data set out of hundreds of data set on hate speech available is like they actually release the individual annotator annotations as well. Like most of the data sets, they just release the final annotations, but they actually release the individual annotations as well, so that we can sort of get individual annotator perspectives and their label choices as well. For example, for guest dataset, they had like 6 annotators. For Dynabench, they have like 20 annotators. But annotators, for instance, for guest was 3, but for Dynabench was just like 1. And these are like some of the uh, characteristics of these annotators. So now let's look at the results. So if we look at the results, so all the models, as we expect, that all of the models are biased towards the majority class. And majority class in this case is a non-hate class, because hate speech is always in like minority. And this AnnoBERT sort of like achieves the highest amount of macro F1 score and the recall uh, of the minority class, right? And then to sort of like demonstrate that it's really helpful, like AnnoBERT architecture is really helpful for the imbalanced data sets. We we did 2 approaches. One is like Dynabench is of course like imbalanced. Sorry, guest data set is imbalanced, but for Dynabench, which was balanced, we sort of like sampled it to make it imbalanced. And then we sort of see the efficiency of AnnoBERT model as compared to the BERT model, which is like the overall F1 score for AnnoBERT is like about 5% higher than the BERT model, which shows that indeed representing different annotator perspectives can be helpful for subjective tasks like hate speech detection. Next, we also look at the disagreement subset, which is like we chose all the subsets of the examples in the dataset that had a disagreement. Disagreement, as in like disagreement among annotators. Let's say 2 annotators annotated that instance as hate, whereas one who annotated as non-hate. So that's like a disagreement example. So we chose all of those like confusing and subjective examples and sort of like trained our model on top of it. So we can noticeably see that like the performance of AnnoBERT is much better for disagreement set as compared to the BERT model. Yeah. And then we also do like some kind of ablation studies to kind of study that whether these annotator embeddings that we obtained from topic modeling approach is kind of efficient or is like good enough for the model or not, right? So for that we try with different approaches. First is the CTR embeddings, which are like fixed or frozen, and CTR embeddings which are unfrozen, as in like which are trainable. So the machine learning model that we are gonna train will also update the CTR embeddings in this sort of setting. And also we experimented with other different approaches as well. Let's say history. History is just like 0 1s and -1s, which is like if an annotator annotated an instance as hate, then it will be like 1. Non-hate, then 0. And if they don't annotate it, and then it would be like -1. So sort of this is just a one hot embedding kind of vector. Whereas these learned embeddings are kind of like randomly initialized embeddings. And then this machine learning model or deep learning architecture tries to learn these embeddings as part of the forward and backward learning process. So as you can see in this, after comparing like all of these different embedding settings for both Dynabench and guest datasets, we can see that overall macro F1 score is the highest for our topic modeling approach. That means it's able to capture effectively uh, different annotator choices and different topics that could be helpful for capturing the subjectivity. Yeah, that's why like we are able to capture the subjectivity of the task with respect to the annotations. Then now like what we can conclude from these two different studies. One of the conclusions is like conversational context really helps the machine learning models in online conversation understanding tasks, and it can be helpful for like various downstream NLP tasks like hate speech, polarity prediction, or maybe like misinformation detection and so on. And as we saw, all of the like ancestor nodes in a conversation tree contribute more than the siblings and the children nodes. Also, for subjective tasks like hate speech, annotators play a significant role. And that's why annotator information can significantly benefit the classification performance. So that's why, like, through this research, we sort of like appeal the community to basically not just like while they are releasing the data sets, not just release the gold labels, but also release the individual annotations as well. And also like if the data sets is like on online conversation, then if like the all of the information of the supports of the parent and child replies is there, then it's also very much like helpful for the machine learning models. But like sadly, in like most of the data sets that are available nowadays does not have this kind of information. Yeah. So we are we are towards the end of this presentation. Thank you all for listening, and I'm now happy to take questions.
Thank you for your presentation. I think someone has a question. Gabriel.
Yeah, I can see the chat. Yeah.
I think we can do the question in audio. Maybe that'll be nicer if you're able to speak.
Yeah, sure.
Just they're washing my building, so it's kind of noisy here. But the question was about the AnnoBERT performance for the disagreement, because I saw there was better performance on AnnoBERT for that set with disagreement. I just didn't really know what better performance in that case meant. Like, did it perform better on finding real hate speech? And then how did you figure that out? Or was it better because you agreed with the majority of annotators?
Yeah, yeah. So in this case, like although the AnnoBERT model is able to capture that subjectivity, right? But it sort of agrees with the majority of the annotators. And by majority here, we are assuming that those are like correct predictions. Yeah. So like the minority predictions, so the minority annotations could be like incorrect ones or like subjective ones, right? So we sort of like ask the model to just predict the majority labels. Yeah.
Thank you.
While they're waiting for someone else to speak, I have a basic sort of a question. So you're in some of the statistics you showed, the accuracies were in the 90s, but your F1 scores were in the 70s. So it's just an artifact of the imbalance. Is that can you go to
Yeah,
the slide?
exactly. So like since the data sets are like imbalanced, so accuracy is not a very good matrix here. And that's why like we sort of like more emphasize on the F1 score and precision recall. Yeah.
And also when you had the plus minuses, they were like, you may have said that, were they like a single standard deviation or? You know,
Oh,
you
yeah.
gave some numbers with plus
Plus
minus. What was
minus.
that?
Yeah, that was like standard deviation. Yeah.
A single standard deviation. Yeah.
Yeah, exactly.
Okay.
Single
Okay.
standard deviation.
And do you have an intuition about how much of the weight of the you know, cumulatively, how much of the weight comes in that range? You know, in that plus minus one standard deviation for these.
What do you mean by the weight?
Like out of 1,000 cases, how many would be in that range? You know, in the in your 69.31 plus minus.
Oh,
You know,
okay.
yeah, I'm just trying to understand.
Yeah.
Yeah,
So
I guess that
actually,
there must be, are there some outrageous outliers, or is it more of a symmetric kind of a distribution?
yeah, so it's like more of a symmetric kind of distribution, wherein like plus minus this donates like, so most of the cases fall under this range, which is like 69.31 minus 0.57 up to plus
Yeah, yeah.
0.57. Yeah, but they can be like some of the outliers as well, but those outliers were like very few only, like in single numbers. Yeah.
And the case, yeah, is somebody else speaking?
Yes, yeah, I have a
Okay, go ahead.
question.
Yeah.
Yeah, so have you ever tried your model on other hate speech data set? Because there are many hate speech data.
Yeah, sure. So as I said, like these are two different tasks, right? So for the first task of like conversational context, we didn't have like any other data set that have like conversation structure, right? Those are like individual comments. And even for the second study that we have like on the subjectivity of the task, we didn't have like other data set that had individual annotations. So there are like a lot of hate speech data sets, but they have just labels of like hate and non-hate. So those are like majority labels. So yeah, that's why we didn't do this like experiment on like other similar data sets.
I think when you talked about your annotators, so in one case you had 5 British and 0 non-British annotators, and the other was 12 and 8.
Yeah.
Yeah. So
So
how did that work out? I mean, did you like at least informally think there was a difference between I don't know how the others may or may not be, you know, good at English, right? So did you notice an effect yourself?
yeah, so actually when we said that these annotator embeddings, so we did not look at these sort of like cultural differences or gender or specifically anything. We just look at their text, and how they have annotated as hate or non-hate.
Mm-hmm.
So we have just added this just for the sake of like the background, but we are not
Mm-hmm.
adding that background information into the model because there
Mm-hmm.
can be like some privacy issues as well. So
Mm-hmm.
we just look at like their annotations, which is just a raw text, whether they annotated as like, let's say, misogynistic, non-misogynistic, hate or non-hate, and so on. Yeah. But I think it can be like really interesting if we can sort of like as a follow-up work, if we can try to map their like cultural differences with the annotations, and we can sort of like derive that, okay, if there are any gender wise patterns or on the basis of nationality there are some such fluctuations, then we can say that, okay, annotations, let's say like by Brits are more helpful for the model than others,
Mm-hmm.
simply because they are like more efficient in English, let's say. Yeah.
Yeah, no, I wasn't thinking of that. I was thinking mainly of even like language competence. Because your
Yeah.
example that you gave with the water, drink water, to me that
Yeah.
sounded like yeah, you know, it sounded weird that anybody would think of that as hate. I just seem like a joke about there are people who just talk about drinking water as the cure for all ills and ailments, and I think this is just a sarcastic remark about those people, right? Not so much about grandmothers.
Yeah, exactly.
Yeah,
But then somebody might say that, okay, it's misogynistic because you are really comparing that person's skin with like old
yeah,
grandma's
yeah,
skin
yeah.
is ugly or something like that, right?
Mhm.
So it can have like multiple
Yeah,
perceptions.
you're right. Yeah, there could be that may not be their intent, but that could be their presumption in a way.
Yeah, yeah,
Yeah.
exactly.
So it could be ageist rather than misogynistic, actually.
Yeah.
Yeah.
I got another question.
Yeah.
So for the guest data set, the labels were misogynistic and non-misogynistic, and then for the dynam, sorry, I forgot the name of the
Yeah, Dynabench.
Dynabench. Yeah, for the Dynabench, it's hate and not hate. Does that hate and not hate includes other types of hate or just misogyny?
Yeah, that's a good question. So, guest dataset specifically focuses on hate against women, and that's why it just have like misogynistic and non-misogynistic labels. Whereas Dynabench sort of like covers other kinds of hate as well, and that's why their labels are hate and non-hate.
Thank you.
Yeah.
Yeah, we have time for some more questions. Anybody, especially those who I know I see people's styles who I know are interested in natural language, but I don't see them asking questions. Your individual annotator analysis, to me, that sounds remarkably like recommender systems from 1999 or before. It was really that the spirit of it, that you can look at, in recommender systems, people are rating movies or products and so on.
Yeah.
Here they're rating sentences, and you're not really asking somebody to go read a sentence, but you're assessing, you're carrying over these correlations from based on one person's assessment, right? Individual assessments, which is what recommender systems also did. Like if you're the kind of person who likes, these three movies, and and somebody else likes the same three movies, and maybe you'll agree on the fourth movie, right? Like that.
Yeah, exactly. Yeah. And that's why we sort of like do our inspiration from recommendation systems. And when I was like doing the literature survey, I sort
Mm-hmm.
of like stumbled upon this collaborative topic regression model, which is like
Mm-hmm.
a topic modeling approach for
Mm-hmm.
similar task. Yeah.
Right. Yeah, I think we have a couple more minutes. If you want, you have a captive audience of about 100 people. If you want to say something else interesting, do a song and dance, whatever, we can do that. And they're awfully quiet. I think only two of them want to ask questions.
Okay, I have a question about the annotations.
Mhm.
So if you can just go back to the slides where you had the distribution for annotations. And specifically about,
Okay.
about misogynistic comments, did you notice any difference between how female and male annotators annotated it? Was there any significant difference? Because this is an inherently subjective task, right?
Yeah.
And I believe based on the gender, it could differ.
Yeah, definitely. So we don't have like this gender specific analysis in our paper, but like I did like my personal analysis. So I could say that based on my observation that females in general, like female annotators, they were more uh like they were more like sensitive towards misogynistic comments than the males, and which we would expect that as well. Yeah. So in general, like people who have experienced something or who are like part of the community, they would be like more sensitive towards that topic. Yeah.
Do you have a concrete example of that type?
I just have like this example, but I don't have like example of that type where
Or
emails
I'm
would
not
say,
saying, yeah, it doesn't have to be written up, but if you remember, or in this case, was the difference uh, in gender of the annotators? Was that the factor?
I don't remember that,
Yeah,
but
yeah.
yeah, I think there would be because it's just like an ageist
Mhm,
and it's just like calling them like ugly sort of
mhm,
thing. Then like a specific gender might get annoyed by these
mhm,
sort of comments. Yeah.
mhm.
But I don't have like specific example in mind. Sorry.
Yeah.
Yeah. Were there any examples wherein like every female annotator would think that this is misogynistic, but every male annotator would think that this is not, like a clear difference between between how the male and the female annotate a given example? Did you come
Yeah.
across?
Yeah. So as I said, there were differences. So there were not that clear distinctions
Mhm.
because I sort of like tried it using some kind of clustering approaches. So when there were no like clear clusters, I would say, but like we could sort of like draw some boundaries. Like, okay, for these cases, females are more susceptible rather than males, and so on. Yeah,
Okay. Yeah, thanks.
cool.
Hey, I have a question.
Sure. Go ahead.
So generally, understanding the conversational context is sometimes apparent and sometimes not. So whenever we receive an output from the GraphNLI architecture, did it
Yeah.
sometimes influence human decision while doing your research?
Influence human decision as in like for what?
Like, did the result from the GraphNLI architecture about the conversational context like sway the understanding of what the conversation is after the result is published by the
Yeah.
machine?
Yeah. So it sort of like predicts whether it's a hate or a non-hate, right? So we observed like at the time of doing like error analysis, we observed that it gives a lot less false positives and false negatives as well. But still, it's not like 100% correct, of course. So still like there were some of the cases where it was not doing like the correct predictions, right? And some of those examples I remember. So those were like in those cases, like these walks are like probabilistic, right? So for example, some of the context is there, let's say in some of the other node which was not selected as part of the graph walk, right? So all these things were there, and that's why there were like some of the misclassifications.
Okay, thank you.
Yeah, you're welcome.
Yeah, I thought maybe Rohan's question was whether you could interpret the findings of the NLI, the context evaluation part of it, not just the total prediction. But maybe that's for
Uh,
later.
I see. Okay. So he was like talking about the
I'm
interpretive.
guessing, yeah, yeah.
Yeah.
Yeah,
Okay.
it was about like whether the interpretation of the humans, like after getting the results from the GraphNLI architecture, was it different from what it was before? Did it change due to the evaluation of the model?
Okay. But I think you never did. You never looked at it again, right? You didn't look at the same data again and sort of re-annotate it or.
Yeah. Yeah. We didn't do like any re-annotations or something, but we do have like an interpretability study as well in the paper, which is like which is like we sort of look at the attention weights, right? And then we can see like in a given conversation for a given node, what are the nearby nodes that have like useful context for that particular task. So with the help of like attention weights, we can sort of look at the node level as well as the token level to try to see like what are the nodes and tokens that are important for a given comment and the given downstream task. So all of these things can later on add to the interpretability of the model as well. Yeah. Yeah, so feel free to check out the paper. Yeah.
Thank you.
Okay, we are nearing the end, as it were, but and I want to thank everybody for showing up and for for your patience and switching from one to the other, both for the speaker and for the attendees. We lost some time in the process, but I think Vibhor had a short enough talk, so we didn't run over as a result. But I hope you'll attend future seminars. We have one lined up on October 27, but I think I expect 3 or 4 before, because we are in discussions with possible speakers for the intervening Fridays as well. So we should see some more of those coming along. And feel free if you want to contact Vibhor. I think the slides will have the information, but you could also write to Soyoung. Yeah, there it is. And she can put you in touch with him. Okay, so let's just thank the speaker and at least a virtual applause if you can